Good morning, everyone. So today we will discuss about cross bedding, or often it is known as cross laminations. So cross bedding or cross laminations are both same thing depending on the thickness of the layers. If it is less than 1 centimeter, then we call them as cross lamination. If it's greater than 1 centimeter, we call them as cross bedding. Previously, we came to know about the ripple migration, that is the sediments in the stock side of the ripples are migrated towards the downstream direction and deposited in the lee side. So this way, due to the migration of ripples due to an unidirectional flow, mainly the cross beddings or cross laminations are formed. Now cross bedding is probably one of the commonest type of primary sedimentary structures that geologists encounter in the sedimentary rock record. If someone try to define crossbedding, then it will be like that um, it's a type of sedimentary structure which consists of internal laminae. Those internal laminae are inclined to the primary or principal surface of sedimentation, that is the bounding surfaces or bedding planes. So basically the laminae are oriented not parallel with the bounding surfaces. If in rock record we find this type of sedimentary structure, we call them as cross bedding. Now previously you study how ripple migrates, that is the grains are moving due to current from stock side and deposited in the lee side. So that is why the stock side is eroded and lee side is depositional surface. So gradually the ripple moves in the down current direction, like this way. So ultimately a ripple or a dune which is previously positioned here, with time they will move in further downstream direction. Now as the stock side is mainly the erosional side, so in rock record the stock side is not commonly preserved, but this lee side is preserved as some fine laminae within the ripples or dunes. Now these laminae are the cross laminations or cross beddings, that is the internal laminae within the ripple or dune. Mind it that if your ripple or dune is preserved, you can observe the ripple mark or dune in the rock record, then these inclined laminae are simply called inclined laminae within the ripple or inclined laminae within the dune. But when you are not able to identify the ripple mark or dune in rock record, but you find these inclined laminae within a rock layer, then only we call them as cross bedding. I'll show the picture in later slides. Now as you can see that in cross laminae, these inclined laminae, mainly the lee side of a ripple or dune is preserved. So if I go to the transverse section of a ripple mark, the mainly preserved part in crossbedding of a ripple mark or dune is from summit point to the trough point. This part is only preserved. Now this entire part has three areas divided by some points. Firstly, the topmost part of the lee side is from summit point to the brink point. This portion is known as top set, and it is, you can see, it is the gently inclined portion. The inclination of this portion is very shallow. Secondly, the steepest portion of the lee side is the slip face of a ripple or dune that is bounded from brink point to the toe point. That is the most steepened part. It is known as foreset. And lastly, again, the lee side becomes gently inclined, that is restricted from toe point to trough point. This portion is known as bottom set. So my entire lee side is divided into three parts: the top set, bottom set, top set, foreset, and bottom set. Among the top set and bottom set and foreset, the foreset portion is the steepest portion. Now, here you can see a cross bedding in rock record. As you know, that cross bedding mainly formed by downstream migration of ripples and dunes under conditions of net sedimentation, which gives rise to cross-stratification or cross-bedding. Now, the term cross-bedding was previously, people called them as current bedding or false bedding. In old literature, you will find the term current bedding or false bedding, but those terms are nowadays obsolete and people used the term cross bedding. Now, as the grains moves from stoss to lee, so my lee side is preserved. Now, during some higher velocity current, when the current condition in which the ripple or dune migrates in a constant rate towards the downstream direction, if somehow a slightly higher energy current comes, then it will cross cut or it will erode the entire stoss side. If I draw a ripple mask like that, then during some higher energy condition, this toss side is entirely cut or eroded. So what is preserved now? My toss side is eroded, the top set of the lee side is eroded, the topmost portion of foreset is eroded. Only thing preserved is the middle and lower portion of the bottom set, middle and lower portion of the foreset, and the gently inclined bottom set portion. So a cross beds or cross laminae essentially consist of the foreset portion laminae and the bottom set laminae. So foreset and bottom set together they form the cross laminations or cross beddings or the internal laminae within the ripples or dunes. Now in this picture you can see that this people is standing above a surface. So this one surface is nearly horizontal and this one is known as a bounding surface or bedding plane. So the crossbed starts from here and goes downwards in a constant inclination, and towards the bottom the inclination gradually decreases, that is become more gentle, and it meets with the bottom bounding surfaces. So you can see that within this bed that is bounded by two bounding surface, the upper bounding surface and lower bounding surface, that is the two bedding planes, you are not able to identify any ripple or any dune, but instead we can identify the internal laminae, and those laminae are bounded by the upper and lower bounding surfaces. So that is why you can say that these are cross laminations, as these laminations are not parallel with the upper and lower bounding surfaces. Instead, they cross cut the upper and lower bounding surfaces at an angle. So that results some characteristic feature of cross lamination or cross bed. The internal laminae are truncated at top, that is, they are sharply abut against the upper bounding surface, and they are tangential at bottom, that is, they're making very gentle angle towards the lower bounding surface. And you can see that this picture depicts a transverse section, a profile section. So in profile section, what we see, a line that is basically a plane in three-dimensional. So a plane has its attitudes, that is strike and dip. Now the dip of these cross laminae or cross beds, that is these internal laminae, this dip amount, that is the inclined laminae angle with the horizontal plane, this dip amount indicates the current direction or downstream direction. That is the, you can say, by measuring the dip angle of these internal laminae, that current moving from this direction to this direction. For this figure, it is from left to right. So the direction in which the internal laminae are dipping, that is the flow direction or current direction. Now from the angle of the inclination, we can predict about the environment in which these cross laminations are formed. Generally, for aqueous flow, that means ripples or dunes formed in a watery environment, this angle is generally below 25 degree. And in aeolian condition, that is in wind driven condition, wind environment, here the angle of cross laminae with the horizontal surface makes 25 to 35 degree. So commonly you can say greater than 25 degree. So by the inclination angle of the cross laminae with the horizontal surface, by measuring this inclination angle, we can predict about the environmental condition, that is whether it is formed in aeolian condition, wind driven condition, or it is formed in aqueous condition, that is watery condition. We can predict about this environment. Now a individual layer, this entire layer which bears the cross laminae, that is called set. In this picture you can see that this top portion, the top layer, it's bear cross beds which is bounded by two bounding surface, that is two blading plane. So this is one set of cross bed. The below layer again consists of some cross beds, so it is another set, and it is also bounded by two bounding surfaces. And the bottommost layer again bounded by two bottommost surface. Within it there are some inclined internal laminae, that is the cross laminations or cross beds. It is again known as set. So each and individual layer which is bounding by two bounding surfaces, two bedding planes, and which contains internal cross laminations, they are called set. And together these all sets, these 3, 4 or n number of sets together, they are called as coset. So there are various types in which you can observe the set and coset. Now another interesting feature of crossbed is found in the sedimentary rock record, that is the dipping of forested laminae, whether it is constant throughout the inclined laminae or varies from top portion to the bottom portion. And there are three cases possible. The inclination of each cross laminae, whether it will remain same throughout the bed or it vary from top to bottom, that depends on the amount of bed load and amount of suspended load. You came to know that these crossbeds are mainly formed by the bed load migration of sediments in the downcurrent direction of ripples and dunes. But there is a sustainable amount of sedimentary particles which are in floating condition, that is in suspension within the flowing medium, if it is river or ocean, then within the water body, if it is aeolian condition, then within the atmosphere or within the wind body itself. There are lots of suspended particles. These are mostly the silt and clay size particles. Now if the deposition during formation of crossbedding is solely or mainly governed by the bed load, that is suspension load is very negligible, then you can see that these sharply truncated cross laminations bounded by the upper and lower bounding surfaces. In both ends of these cross laminae, you can see that they are sharply truncated or sharply abut against the top and bottom bounding surfaces. So this kind of crossbeds forms when they are mainly formed by bedload sediments, not by suspension materials. That is, suspension sedimentary deposition is very negligible or almost absent. Second case, when there is a ample amount of suspension deposition. So initially this is my foreset orientation. If I draw a ripple, my ripple mark will be like that. Okay, so this toss side is eroded, so no question of bothering about the toss side. Now in the lee side, this is my foreset portion. Now in a medium, flowing medium, whether it may be water or it may be wind, that medium affects mostly the topmost part of the ripple or dune. The trough region, this portion, the trough region is basically relatively calm environment. So whenever suspension fallout occurs, that occur in the calmer situation, that means where the energy condition is very low, very negligible. So mostly the suspension materials, they are deposited in this trough region. Okay. And that is why ultimately with each foreset laminae which are in high angle in its top part but towards bottom part, due to the deposition of sufficient amount of suspended materials, the bottom part, that is towards the bottom side, they becomes very gentle. So there is in the bottom portion there is uh, some bed load deposition, and above that some suspension material. So ultimately the cross laminae is carved and becomes more gentle towards the bottom part. So that result a sharply truncated top with the upper bounding surface and a asymptotic bottom, that is a gently inclined or gently cutting bottom laminae towards the bottom side, towards the lower portion with the bottom bounding surface. So when suspension material is high or a considerable amount is there, then the inclination of these cross laminae becomes gradually gentle towards the bottommost part, because that is the trough region of a ripple or dune where a calm condition exists. So all the suspended material, they basically deposited along the trough region of ripple or dune. Now if the suspended material amount is increasing with respect to this part, so in the third case the suspension material is very high. If this happens, then the suspended material will deposited all along the ripple mark, that is in the crest region and in the trough region, all the surfaces. So that result your preservation of the top set also. So as the suspended material is mostly of silt and clay size particles and they are very cohesive, as we know. So due to this cohesiveness nature of the suspended materials, when they deposited over the crest portion, they will resist further erosion of the crystal part, that is the top set portion. So my entire top set portion is preserved, and that results preservation of the top set, fourth set as well as the bottom set, and ultimately they will result a sinus or sigmoidal pattern of crossbedding. So this is known as sigmoidal crossbedding. So you can see that depending upon my amount of suspended material deposited during migration of ripple or during migration of crossbed, my inclination of cross strata, my inclination of cross laminations, they will change with the amount of suspended materials. So when suspended material is negligible, then the cross stratas are angular. When suspended material is considerable in amount, then the inclination of cross laminations change. They become more asymptotic towards the bottom. When there is a high amount of suspended load, then the cross strata becomes sigmoidal or sinus shaped. Now it was observed that during the formation of cross strata, many times the energy condition is changed. Energy condition does not remain fixed throughout the formation of the uh, cross strata or cross beds, because it's a natural condition, so energy condition cannot be remain fixed for the entire amount of time. Now in the first picture you can see that the distance between two successive cross strata is not constant. In some cases they are very closely spaced, as you see here, and in some places they are very distantly placed, as you see here. This results due to tidal cyclicity. You know that tidal effect on Earth's water body is resulted due to the attraction of sun and moon. Now when sun, earth and moon, they occur in the same line, then the attractional force of sun and moon act together over the Earth's water body, which faces these celestial bodies. So in this time, when sun, moon and earth are in a line, at that time the effect of tide is maximally observed, and this is known as spring tide. So within a month we can observe two times, that is the Purnima, full moon, uh, and new moon condition. So these two times the effect of attraction of sun and moon on Earth's water body is maximum. This is known as spring tide. But during its rotation around the Earth, moon comes twice within a month in position which occur perpendicularly to the connecting line of Earth Moon. So Earth Sun. So this is the Earth Sun line, and you can see moon occur perpendicularly to that line. So at that time the attractional force of sun and the attractional force of moon, they try to diminish each other, and that is why the effect of tide during this two time is minimum, which is known as neap tide. So within a month two times we can see the effect of spring tide, and two times we can see the effect of neap tide. So as you see that in spring tide the effect of attractional force of sun and moon is maximum, so the tidal effect on the Earth's water body is maximum, that is more amount of bulging of Earth water surface, that means more amount of water, that means more amount of tidal energy. So that results distantly spaced cross laminations in the rock record. So due to high tidal effect, that is spring tides, there is the cross laminae occur more distantly spaced as the energy condition is high during that time. So more and more amount of sediments are carried out. But during neap tide, the energy condition is low because the attractional force of sun and moon try to diminish each other. So tidal bulging of earth surface water is low. So that is why my cross lamination spacing is narrow, that is they are very closely spaced. So these closely spaced cross laminations indicates the neap tidal cycle, that is known as neap bundles, and these distantly spaced cross laminations, they are known as spring bundles that results from spring tide. So together one neap bundle and one spring bundle, they formed a entire tidal bundle. Okay, that is a half month period of deposition. So this is the tidal bundle. So from the variation in thickness of the internal laminae, that is the cross laminations, you can predict about the tidal cyclicity within the rock record. If it is distantly spaced, then it is formed due to spring tide. If it is very closely spaced, then it is formed due to neap tide. Now, as you know that there are many situations when changes in flow velocity or flow depth occurs. Now suppose in a condition when due to ripple or dune migrations, these kinds of cross beds are forming. Now, if in a certain some higher amount of energy comes, so instead of simple migration of ripples and dunes from its upcurrent side to downcurrent side and forming these cross laminations, they will entirely erode the thing. That is, there will be no deposition, so they will erode. And after this, suppose this is a flash flood, so suddenly a flash flood came, and that will uh, be due to the higher amount of water come when the energy condition is also very high, and that will result erosion of this part. No deposition occurs. But after few hours or few days, when that certain phenomenon or certain event is over, then again the previous condition exists, and again the cross laminations are forming like the previous way. And in rock record you can see that these two events, which is separated by this abnormal event, certain abnormal event, they are together bounded by within a bed, that is single bounding surfaces. But there are two events happened in two different times, that is these cross laminations and these cross laminations, they are separated by an erosional surface, a certain erosional surface. This erosional surface is known as reactivation surface. It is a certain event due to certain change in flow velocity or flow depth. Instead of deposition, erosion occurs, and after this event again the previous conditions resumes, and again the crossbeds are formed. So this small scale erosional surface within a single bed, that is found within the cross laminated bed, cross laminated unit, we call them as reactivation surface. And you can see that this reactivation surface is not parallel with the cross laminations. That is, this reactivation surface sharply cross cuts the cross lamines. And also this reactivation surface is not parallel with the upper and lower bounding surfaces. So on the basis of that, on the basis of cross-cutting nature of this erosional surface with the upper and lower bounding surface as well as the internal cross lamines, we can identify them in rock record. So reactivation surface is a certain change in energy condition depicting event. Now, if I try to classify crossbeds, then what are the different types of crossbeds? They can be classified into two groups. The first one is planar, where the bounding surfaces, that is the top and bottom bounding surfaces, are both planar. And the second one is the trough cross-stratification, where the bounding surfaces, that is either it is both the bounding surfaces or one bounding surfaces is not planar, instead it is curved, then we call them as trough cross-stratification. So in the first step the bounding surfaces are planar, they may be parallel, they may be not parallel to each other, but both the bounding surfaces are planar surface. In the second case, the bounding surfaces are curved. You can see here that if some cross strata exists here, this cross bed is bounded by two surfaces, but the surfaces are not a planar surface, it's a curved surface. So this type of cross bedding is known as trough cross bedding. Now I go to So the first type of planar crossbedding is known as tabular crossbed. Tabular crossbed is a type of crossbedders in which the bounding surfaces are planar. So it's a type of planar crossbeds, and these bounding surfaces are parallel also. So you can define tabular crossbeds as a type of crossbeds in which the bounding surfaces are planar and parallel. Now, if the bounding surfaces are not parallel to each other, so the bounding surfaces are planar but not parallel to each other, then we call them as wedge cross stratification. So you can see the thickness of these beds here and the thickness of these beds here is not same. That is why we call them that the bounding surfaces are not parallel. In this block diagram, you can also see that the thickness here and here is not same. Also here is not same. So this individual bed of cross stratification is known as set, and successively one or two more than one sets composite of coset. Third type, that is where the bounding surfaces are not planar and parallel. Here you can see that the bounding surfaces are curved, the bounding surfaces are curved. So in this type, the bounding surfaces are not parallel and also planar to each other. Now, the planar crossbedding are mostly formed from the straight crested ripple migrations, whereas the trough cross stratification are formed due to migration of sinus or cuspate or lunate linguade ripple migrations. So that is basically for 2D ripple migrations, your planar crossbeddings are formed. For 3D ripple migrations, trough cross stratifications are formed. These three, there are two other types of crossbedding observed in nature. Here you can see in rock record that this one is one bounding surface, the bottom one is another bounding surface, and within this there are numerous cross laminae. But you can see that the inclination of the bottom layers cross laminae inclination direction, and in the top layer there are also some cross laminae, but the inclination direction of these two cross laminae are opposite to each other, as it looks the midrib of a fish from where the bones are diverged in two directions. So basically, scientifically, the cross strata orientation, cross lamination orientation in two successive beds are opposite to each other. We call them as herringbone cross stratification. Keep in mind, for calling herringbone cross stratification, we have to consider more than one bed of cross lamination. Here we consider two beds, but previously for tabular, trough, wedge cross stratification, we are considering only a single bed which depicts cross stratification. And the final one, that is known as Hummocky cross stratification. This is basically an undulating bed form. Uh, you can see the ups and downs, and obviously these are cross-cutting with the bounding surfaces. These dark colored lines are the bounding surfaces, and you can see the internal laminae are cross-cutting with the bounding surfaces. So this is formed from by some, or this is defined by some undulating surfaces which are basically thought to be formed by wave generated oscillatory flows or the combination of current and wave together with some effect of storm activity. So mostly these kinds of Hummocky cross stratification are occurred during some storm event. So the elevated portion of this Hummocky cross stratification, that is the bulging portion which is convex up, that is known as hummocks, and the portion that is slightly depressed portion which is concave up, that is known as swell, and the inclination angle is generally 10 to 15 degree. So this is known as Hummocky cross stratification, or you can abbreviate it as is HCS. Sometimes in rock record people only found this swelly cross stratification. So instead of saying that Hummocky cross stratification, people also use the term swelly cross stratification. You can see that the thickness of individual cross laminae are decreasing increasing towards the hummocks. That is, sediments are dragged from the soils towards the hummocks. Uh, so all the depressed portions from the swell portions, they are dragged towards the hummock portion, and that is why the heap of sediments or bulging of sediments occur here. But it is not so simple. It's a complex process. Uh, Basically, it is a combined process formed due to wave, uh, current, and uh, storm activity. Now, as you know that the trough region is the most calm condition within the entire feature of the ripple mass. So my flow is from left to right, that is toss to lee. Flow directly hits the toss side and mostly in the crystal part. Okay, so this portion is highly affected by the flow, this topmost part here, and the trough portion, which is the lowest elevated portion, that is the calm condition. Now it is often found that in these trough regions some suspended clay particles or mud particles, they are deposited, as I previously told you during the uh, changing inclination of the crossbeds. But if crossbeds not formed and there are some suspended clay particles which deposited in the trough regions, so rock record, you can see that there are ripple marks, and within these ripple marks these thin streaks of mud, mainly within the ripple troughs. So entirely sand dominated environment consists of several ripple marks and some thin streaks of mud within the ripple trough. That is, these muds are mainly concave up situation. So this kind of bedding or this kind of lamination is known as Flaser bedding or Flaser lamination. Now if the mud portion gradually increase, so that indicates alternating sand, that is alternating ripple horizon with alternating mud. So you can see in rock record that alternate sand and mud deposits, and as the cohesiveness nature of mud is high, so after deposition of mud, the erosion is very negligible. So during the formation of this kind of laminations, after the formation of ripples in the uh, sand bed, when mud settles, they try to follow the curvature of the previously rippled sand bed. So the mud beds are also formed in a curved manner. These kinds of beds with alternating curved surfaces of sand and mud are known as wavy lamination or wavy bedding. Now in the last case, when the mud proportion or mud deposition is extremely high, In that case, you can find some isolated sand ripples are floating within the mud. Sometimes they are connected or sometimes not. They are totally isolated. It looks that they are floating, these uh, white colored portions, these sand bodies, these bodies. They are totally isolated, they are totally floating. Basically, these are the ripple marks. And the mud deposition is so high that the connectivity between two successive ripples is lost. So in rock record, it seems that the sand bodies are floating within this mud deposition. This kind of lens-shaped sand bodies are known as lenticular bed or lenticular laminations. So you can see that deposition of mud within a rippled terrain, that is mainly within the rippled trough, starting the mud deposition within the rippled trough, it forms first Flaser bedding when mud deposition is low, mainly restricted as streaks within the ripple troughs. Then mud deposition increase and deposited all over the ripple surface, that is both in crest and troughs, formed wavy lamination or wavy bedding. And ultimately, when the mud deposition is extremely high, then it looks that the sand bodies, that the rippled sand bodies, they are floating within the mud deposition. So then we call them as lenticular bed or lenticular lamination. Thank you.